Hello, everyone. I would like to welcome you all today to today's presentation. My name is Arbrecht. You may know me from last week's MIU. Before we begin, I have a few important announcements to ensure a smooth session. First, I want to thank you that you're joining today. Please remember to keep your microphones muted throughout the presentation to minimize background noise. We also kindly ask you to turn off your cameras as we started a video recording of the session. Lastly, if you have any questions, please use the hand symbol to indicate your interest, or feel free to ask your questions in the chat. At the end of the presentations, we will hopefully answer all of them. Now, without further ado, I would like to hand over the floor to my colleague, Paul Koch from the research team Maritime Informatics, who will hold a presentation with a nice title of Charting Autonomous Navigation, Filling the Gaps Between Tech and Regulation. Thank you.
Yes, thank you, Arbrecht, for the introduction, and welcome to everyone. And thank you for joining today's MIU. So the topic, as you see on the title, is a bit about autonomous navigation and regulation. I will cover a few topics on what we see as current challenges here at Fraunhofer CML and how we think these can be solved, especially when we're thinking about bringing innovative ideas into reality, which, well, unfortunately or fortunately, however you view it, require the verification of those same techniques, which is a challenging process. So what will we go over today? We will talk a little bit about the current trends in autonomous navigation to see a little bit what's going on, where the technologies are and what they are. What are the goals and the purpose of regulate and validate? So why are systems regulated? How are they validated? How is this process looking like at the moment, and where are the challenges? We will talk about new approaches of assessing the safety of MAS. As one example, I mean, it's a conglomerate of technology, but I think MAS is the term everyone is most familiar with. And in the end, I will talk a little bit about some recommendations for agencies and organizations, and of course also for companies who create these technologies and innovate in the field of maritime autonomous navigation. This whole presentation is based on these two studies I've linked here. So if you want to read further on those, you can kindly visit the link. If you want to know more about these, you can of course also contact me after the presentation and I can send you the studies directly. So without further ado, current trends in autonomous navigation. So which technologies are actually emerging? And I think there are a few interesting categories we can look at. We have like a machine learning based detection of ships and hazards. So what you know most likely as camera systems that can detect objects in the water, other ships. These systems are also often used to like extend the situational awareness on the ship's bridge to kind of make this comprehensive situational awareness system, as you might call them. Of course, these systems are also often like a cornerstone for like a full integration, so autonomous vessels as participants in traffic, or partly autonomous systems who are like installed on the bridge to alleviate a little bit the load on the officers. A few examples of those I've listed here. So we have a few camera systems. In the bottom right corner, we have, for example, the B0 system that we developed here at Fraunhofer CML as one example of an autonomous or partly autonomous system, which was designed to like make a ship able to navigate autonomously for up to 6 hours. And of course, all these systems face the same challenges that, of course, like building a prototype is nice and easy, but bringing it into an actual product or building a business case out of it requires regulation. And that's when you identify that the current organizations responsible for this are kind of also a little bit under the water on how this will actually go in the future. And if you look at what's going on in the field, you see that this will be an increasing challenge, let's say. So our two studies that we've done identified over 18 active manufacturers, and I mean this is from 2023 2024. This will be even more by now, and you can see on the graph on the left side that if we look at the patent registrations for any type of technologies in the maritime autonomous sector, we can see that it's nearly exponential. And if you look on the right side, what kind of sensors and data types are these manufacturers actually using, you see it's like a wide variety of technologies that is there, where you kind of already see that this field is highly complex, and it's not like, oh, this system is just, I don't know, displaying a C chart or using a simple camera, but it's more often like a really, really complex system using a wide variety of data sets, which makes this whole regulation challenge even more complicated than it already is. So when we look at how to regulate these like emerging technologies, or how they can be tested by an organization or by the manufacturer beforehand, what do we have to take a look at? Well, there's of course a wide variety of possible architectures. I mean, today we talk about AI systems, but I mean, I already put it in quote, that's really like, it can be everything and nothing at the same time. It's really hard to pinpoint it to a specific technology. And of course, we also don't want to pinpoint it to a specific technology, because that would hinder innovation. I mean, that's the last thing that we want. But when we look at all the possible technologies that are there and all the possible ways you could implement them, you see that the bandwidth of data that you could potentially utilize kind of is unlimited. Could be camera data, so it could be, I don't know, pixel data of a camera frame. It could be data from a situational awareness tool, maybe from a radar. Maybe it's position messages from an AIS receiver. It really is, I could go on and on. So what I want to say with this is that just pinpointing like regulating autonomous system to like it uses this and that kind of data is very, very hard and very complicated. So it will be very hard to kind of regulate these systems from this point of view by just saying, oh, you use this and that kind of data, because this will also just hinder innovation in the end. So where we arrive at the end is that all the testing must be model agnostic and future proof. What does model agnostic mean? In simple terms, it's just like however we want to test and verify future autonomous systems in the maritime domain, it can't rely on knowing how the system works. It is more in the direction of if the system works and if the system behaves predictably in all situations that we can think of. And this will be, from our point of view, at least as Fraunhofer CML, must be the way on how we approach this. Because if we look at what kind of, let's say, framework documents we have out there, and I mean, we're in Germany, we love our regulatory documents, it's kind of a mess and kind of really complicated, but also not exhausting and not really helping at the moment. Like if we look at what kind of DIN spec documents we have, I mean, these are not even real normative documents. These are just kind of proposals at some points. So you see that we have the DINs in the middle. We have, of course, our study as one approach that we did. There is the EU AI Act, which imposes regulations from the outside. So just some pressure on whatever we do. It must follow a certain set of properties, and it must adhere to these. We have some more regulations out there that kind of tell, okay, for different use cases, you can do this and this kind of procedure, but this is not very exhaustive and is not really specific to the maritime domain. It's kind of trying to be very generalistic, which is also not very helpful. There are some guides out there, like to designing trustworthy AI, for example, also from other Fraunhofer institutes, which kind of try to bring a more comprehensive picture, but they're also not very, let's say, detailed and more an overview document, if you want to call it. If you look at like what is there for actually developing and testing the systems itself, so let's say I use a specific technology, like a specific machine learning algorithm as one example out of many. There are, let's say, ISO regulations or ISO standards, to be more precise, that you could utilize, but they're also just covering a, let's say, part of your technologies and, well, by far not all of them. So you already see that what's out there of the available regulations is not really helpful and by far not enough to build a process out of it, which is on the one hand model agnostic, so works for all kind of approaches, but is also somewhat standardized and generalistic enough that you know what you're up to, and it also not in a form where it's very extendable, to put it in simple terms. So in the Verify study, we kind of thought about a new approach to this regulate and validate challenge, because we thought about, okay, I mean, in the end, it's all about the communication between a manufacturer building a system and some kind of regulator that wants to look at the system and in the end kind of put a stamp on it to be like, yes, I'm sure that the system performs how it should be. So we kind of thought about, okay, there must be two kind of concepts. So there will be a safety concept. This is that whatever a manufacturer comes up with complies with a certain procedure so that the regulator can take a look at the system in a somewhat standardized way. And we want to achieve this standardization of how the manufacturer speaks with or communicates with the regulator via a modularization of whatever system the manufacturer has come up with. So the idea is that however complex your system may be, your task as your manufacturer is that you divide it into smaller components that can be individually tested, and then the regulator can take each of these components, put a certain set of data in, and gets out a certain output on the other side. And by giving it, let's say, enough test cases and or scenarios that the regulator is confident that the system performs as expected and performs, let's say, deterministic, then you can be sure that your certification is reliable enough and that your system is tested and you can credit it and like give your stamp of approval on it so that the system can be used, let's say in the real world. So kind of drawing this a little bit more with some figures here. So let's say we have a system on this left side from the manufacturer. He has built some kind of AI system. I try to keep it vague here so that you see that this works also when it's not clearly defined what a system must contain. Because in the next step, the manufacturer is responsible for performing this modularization. For example, if he has really an autonomous decision solution for a ship, he has to be like, okay, I have to divide it into maybe a planning component, a decision component, an assessment component. This is just an example. The only important thing is that in the next step, any institution, any regulator, whoever wants to take a look at the system can come up with data for testing due to augmentation, simulation, synthesis, wherever he gets the data from, puts it into this module, so kind of this input-output test. And in the end, he is like, yes, this is the data or the output I was expecting. So maybe like we give the system a kind of traffic situation, and yes, it changed the course to starboard, yes, it avoided the other ship, yes, it kept a safe distance, and it did this for a wide variety of testing scenarios. We can put, let's say, the check mark on it and be like, yes, the system is verified, assessed, it does what we thought it would do, and also it does it in the way that the manufacturer said it will do it. Or we can be like, no, we gave the system some scenarios that we came up with that comply with what the manufacturer said the system would be capable of handling, but in our tests, it didn't do it. It failed, maybe it produced undesirable outputs, or it was unpredictable. So then the regulator can go back to the manufacturer and be like, here, in this test cases, your system failed. So he has to do amendments, do new tests, and then the whole process starts again. And I think what you kind of can already see that this process is independent on knowing how the system works. Because on the one hand, manufacturers will be very adamant on not sharing their intellectual property. So they're kind of protected in that way. But in the end, they have to have a working system because, well, it will probably be tested with unforeseen data, which still complies with what the system should be capable of. So if the system is not built well enough, it will probably fail those tests and not get the classification or the stamp of approval that the manufacturer needs. And one specific example that we're kind of working on at the moment to start somewhere is this whole challenge of, let's say you have a system that is performing autonomous navigation, and you need a lot of traffic scenarios. The problem is, yes, the standard idea up until now would be that we define a set of test scenarios. Maybe we give 70% of those scenarios to the manufacturer. We keep 30% for ourselves, kind of as a validation data set, and then we test the system on this, on these example scenarios. The problem is that this is very rigid, not very extendable. So we came up with kind of developing a framework, and we call this, it's a little bit intermediate at the moment, but it could be like a nautical scenario description language that allows us to build up scenarios either from historical data, from damage reports. We could create custom scenarios. You could create, let's say, language models that can convert traffic scenarios into this descriptive language. And we use this language to build data, and data in this term means example scenarios of what a current traffic situation could look like. And this we can then replay to any kind of system. So you take this NSDL, so this descriptive language, you build up some kind of scenario that you can think of, or you can do it in an automated way, which is kind of the idea behind. So you can build hundreds or even thousands of different scenarios very, very quickly. And these you can give to the system in whatever format as NMEA input, or you can generate other data out of it. I don't know, 3D images, synthesized images, whatever you want to do from it. Give it to your system, derive some KPIs from it, and then you can see if the system does what you expected or not. So I have it a little bit more as an example that you can see it here. So you can kind of, in simple terms, write down what should happen in a scenario. Our approach generates the whole data that normally would be very hard to procure because you would have to, I don't know, search through AIS data or come up with these trajectories by yourself. And then you can just test your system on it and see if it works or not. And the real benefit comes into play when you scale this up, as I said, for like hundreds or even thousands of different scenarios. And if you do this for a big variety of different scenarios and different combinations of scenarios, you can pretty quickly and pretty exhaustively test a system just by giving it all these different scenarios and seeing how it behaves without needing to know how the system comes up with a certain solution. But you are sure it works because you just gave it so many scenarios and you saw and you're kind of convinced that it works safely and predictably. Just one example, of course, there are many, many more applications that you could build on top of it. So also circling back a little bit to the studies I linked in the beginning, based all of these challenges, we kind of came up with some recommendations for actions. These are, of course, mainly for the organizations, agencies, regulators out there to kind of what they should keep in mind when developing these processes to regulate and to validate the future AI systems in the maritime domain. So as I said, it should be model agnostic. There should be no rigid processes. It should not be like if your system is a deep learning based object recognition algorithm, it takes this procedure. If it's a simple decision tree, it takes this procedure. It shouldn't be like this. It should be more like you give us a system, we test it based on your input and output specification, and you either can convince us it's safe or we do not give it our approval. And this kind of leads to the question, we want to see whether a system works and we are not interested in how it actually works. So the specific implementation should not be the core matter of how a system works. It should more be, can you convince an outside participant, like an agency, that it works under all circumstances. So what are some ways that you could achieve it, of course? Well, you can standardize not the procedure itself, but you can standardize a little bit, okay, how can input and output data look like? So if you work with like vision-based systems, or for example, when you procure the data for your situational awareness or whatever system you may have, you can of course use either standardized protocols that are out there, like an MIA protocol, or it can be thought of defining some new, little bit more rigid definitions of how, for example, camera data can look like, or something like this, to kind of ease a little bit this, like, okay, we feed it a standardized type of input data and a standardized type of output data. The second way that you could think of is also that you build some pipelines for having on-demand provision of real and of synthetic data. One way you could do this, for example, would be what I just described, using, for example, some simple descriptive language that we've built, which eases the creation of, let's say, hundreds or thousands of scenarios. You could use a few more modern advancements to also maybe test, for example, vision-based systems. In this case here, we have some example images of using transformer-based architectures like the Dolly model or other image generation models, whatever they are, diffusion models, whatever you can think of, that are able to generate new unseen images. Or for example, in this case, it was a prompt of ships on the horizon, and you can see that these images are fairly convincing and close to the real world, without having the risk that maybe the manufacturer has already used these images to let's say, build his system, which would then make any tests not really valid anymore. And of course, we would highly push for that the agencies, at least in Europe, kind of communicate with each other. That will also make it very easy to build needed processes and generate the needed data easier and quicker. And I think it will also help if these agencies work a little bit together, because at the moment I think that the different countries are at different stages on how they can validate these systems. And I think if we look at Germany, we still have quite a way to go, unfortunately. But that's more or less all from my side for today. I hope it gave you some inspiration on how this can go in the future. Of course, if you want to talk about or want to talk with me about it after this presentation, feel free to reach out to me, either via email or via LinkedIn. Please don't call me. I don't know why this phone number is still there. But yeah, I would be happy to talk to you and also send you the studies that I linked in the beginning.
Yeah, thank you, Paul, for your presentation. With a look on the watch, we shouldn't push the time too much right here, but there are also no questions in the chat right now. Also, nobody is using like this hand gesture. So I have a few questions, but I'm just focusing on a shorter one, on a yes or no question. So let's say I have a system and I want to get it tested. Can you help me with preparing it for a procedure like this?
Yes, we're currently building on like what I've presented here. We are, of course, like in the real implementation much further already. And we are kind of trying to build up procedures on testing these systems for manufacturers before there is a, let's say, an official way to do it, just to help them kind of get into the process. So you can, of course, also reach out to us if you want to talk about how to test your specific system if you have one.
All right, Paul. Thank you. And yeah, just for your information, next week's MIU is about digitalization of a port model. So feel free to also join there. Thank you for your time and have a nice
One more thing. Please also note that we will host the ICMAS 2025 this year. So you can either scan the QR code or look on the website. And we would be happy to welcome you at our facilities in Hamburg. Thank you very much.
Bye.